right, let's get going. Ah, come on. All right. Tonight, we are doing bonding. Bonding is a big one. Bonding is a big unit. It might take about a video and a half to do all of it because I want to do like types of bonds, principles of bonding, drawing Lewis dot structures, all that stuff. So this might bleed into the next video a little bit, maybe. We'll see. So, just a little bit of review. Bonding is always going to involve compounds, which are substances. They are chemically combined, and they are combined in what we call fixed ratios. So, for example, like H2O, if you change the ratio of hydrogens 2 to oxygens 1, if you change that ratio, you don't have water anymore. You have a different substance. So we're chemically combined, we have fixed ratios, and when these things form a compound, they form a bond. And the bond is all about the valence electrons. So these bonds are formed as a result of a chemical reaction of some kind. And we'll go over types of reactions later. But when you form or break a bond, you're forming new substances. So when you're forming a bond, let's say you're forming H2O, this is when the acronym BARF comes into play. So BARF stands for breaking absorbs. And when we say absorbs, we mean absorbs energy. So breaking a bond absorbs energy. When energy is released, you are forming a bond. So in this case, with H2O being formed here, you're taking two separate atoms, two separate diatomic elements, and hydrogen and oxygen, bringing them together to form water. This is going to release energy. Which means the opposite is also true. So, when you break a bond, if you were to do this backwards, break that water bond and form the elements it's composed of, that would absorb energy. So this reaction here absorbs energy. But I'm really going to end up focusing on bonding. And the key with bonding is anytime these bonds form, we want to obey the octet rule, which means every atom wants 8 valence electrons. So we are trying somehow, some way to get to 8 valence electrons, and each atom is going to do that a bit differently depending on what it's bonded to. You can do it ionically, where electrons are transferred from one atom to another, or it can do it covalently, where each atom will share their valence electrons. So, the first one I am going to do, actually the first thing I'm going to do before we get into bonding is I'm going to start dot structures of basic atoms. So to draw just your dot structures, I don't know why I'm leaning to the left here, of atoms and ions, because I know the Regents likes to ask you to draw ions. So if you go to the periodic table, pick any element, it doesn't matter. We can do oxygen. Why not? Oxygen seems like fun. So let's zoom in on oxygen here. So when you go to the bottom left, that 2-6 is its electron configuration, meaning it has 2 electrons in the first energy level, and then in the second energy level, it has 6 electrons. And the last number in its electron configuration are the valence electrons. So like nitrogen has 5 valence electrons, fluorine has 7, carbon has 4, oxygen has 6. So when you draw the dot structure of oxygen, all you're doing is showing its valence electrons. So if you draw oxygen as an atom, meaning no charge, you want to draw oxygen with those 6 valence electrons. So I usually say start at 12 o'clock, then go 3, 6 o'clock, 9 o'clock, and then come back around and finish what's left over. So 1, 2, 3, 4, 5, 6. So that's oxygen's dot structure as an atom. Now when you draw oxygen as an ion, you need to look at its charge to determine what its how many electrons it's going to gain or lose. So oxygen has a charge of -2. And a negative charge equals a gain of electrons because electrons are negative. So a negative charge means you have gained electrons. If you gain negatives, like an electron, you become more negative. If you lose an electron, you're losing negatives, you become more positive. So if I were to draw oxygen's dot structure as an ion, so now I'm going to draw oxygen with its charge, you will do, its normal configuration is 2-6. So normally it has 6 valence electrons, but that -2 means it's gained 2 electrons, which means now it has 8 valence electrons. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. Now some students will stop here. Do not stop here. You have to show the charge. If you're asked to draw an ion, you need to show the charge because ions are charged. Atoms are not. So put the charge on there, -2. A lot of teachers will also draw these in brackets. And you can draw it like this if you'd like. Because, and the reason we draw it in brackets, it's just convention. Oxygen is not going to just gain electrons from no one. These electrons don't just appear out of nowhere. Someone must have donated these electrons to oxygen. And that's what's happening all the time in your redox reactions. When most of you either are currently doing or recently wrapped up the unit on redox, oxidation and reduction, the electrons that are being gained in reduction and lost in oxidation don't just appear out of nowhere. The oxidizing atom will donate its electrons, Leo, lose electrons oxidation, to the other one that's being reduced. So the reduced one is always gaining electrons from the one that's being oxidized, who's losing the electrons. So we put these brackets because when you end up drawing ionic compounds, you usually show these brackets, and one atom will lose electrons and one atom will gain electrons. But as long as you put the charge and correctly show how many valence electrons it should have, you should be good. All right, let's do fluorine. Fluorine's ground state electron configuration is 2-7. So fluorine as an ion, fluorine as an atom will have 1, 2, 3, 4, 5, 6, 7. That's a fluorine atom. Fluorine as an ion is charged -1 to show it gaining 1 electron. 1, 2, 3, 4, 5, 6, 7, gain 1, 8. Put its charge, -1. So we got our our atom and our ion. Atoms are not charged. Ions are charged. Okay. Now let's draw ionic bonding. So, an ionic compound is always a metal and a nonmetal. So, let's pick a metal and let's pick a nonmetal. So from yesterday, everything to the left of this staircase here, besides hydrogen, hydrogen's a nonmetal, all of these ones to the left are metals. So I'm going to do calcium. And then everything to the right of the staircase is a nonmetal. I'm going to do chlorine. The principle of an ionic bond is that they transfer electrons. Electrons are being transferred in ionic bonds. So, what does that look like? Sometimes you might be asked to draw these. So I'm going to draw calcium in the ground state. So calcium's electron configuration is 2, 8, 2. No, 2, 8, 8, 2. Yeah, 2, 8, 8, 2. 2, 8, 2 is magnesium. So, calcium normally has 2 valence electrons. And we're going to keep in the back of our minds that calcium as an ion is +2. Chlorine is 2, 8, 8, no, 2, 8, 7. 2, 8, 7. So chlorine normally has 7 valence electrons. But when it's paired ionically, when chlorine becomes an ion with a metal, chlorine only has 1 possible negative charge. Metals are always positive. If you look at the periodic table, when metals form an ionic bond and make an ionic compound, they become ions. Ionic compound. That means they're charged. And if you look at metals, metals are always positively charged. When you look through all of these metals, you will not find a negative charge. So when you find chlorine, chlorine has positive options, but when it's with a metal, when it's bonded ionically with the metal, it can only be that -1 because the positives and the negatives need to cancel out. Again, you practice this a lot with oxidation states. We're going to keep in the back of our minds that chlorine would prefer to gain an electron in an ionic bond. So, when calcium and chlorine bond, one will transfer its electrons to the other. Since metals prefer to be positive and the nonmetals prefer to be negative, the nonmetals are going to gain the electrons from calcium. So calcium, since it's got that +2 charge, has 2 to donate. So calcium is going to try to donate or transfer 2 electrons to chlorine. But chlorine only needs 1 more to become a stable octet to have those 8 valence electrons. So what does that mean you need to do? Well, when calcium and chlorine bonds, that means we need a second chlorine to accept that second electron from calcium. You can also kind of figure this out from naming and formula writing, which was yesterday's video. If calcium is a +2 charge when it forms a bond with chlorine, and you crisscross down the numbers, you get CaCl2. I need 2 chlorines to balance out the +2 charge of calcium. So, when these form a bond, I'm going to draw it like this. You can have 1 chlorine over here, calcium, and another chlorine. And these electrons are going to transfer to the chlorines. So you'll get, and I'll just show the brackets because that's just convention. A lot of times you will see ionic compounds in brackets. You get the chlorine over here with that electron gained. You can show these electrons as dots. You can show them as X's. You can show them as smiley faces, as long as you're indicating the electrons being lost and gained in some way. Calcium now has lost both of its valence electrons. And then chlorine over here also gained that other one from the calcium. And this is how you show ionic bonds, okay? You show ionic bonds like this because the bond is the attraction of opposite charges. Okay? So these bonds are formed from that attraction of opposite charges, those pluses and minuses. You might also see it worded as electrostatic attraction. So when these things bond together, they have that electrostatic attraction, that attraction from the opposite charges, and they form that bond. Now, ionic compounds, if you watch the video from yesterday, do have really high boiling and melting points, but the bonds itself are not that strong. They're easy to break apart. And you can do that just by dissolving in water. As soon as you dissolve calcium chloride in water, it's just going to split into its individual ions, making this bond not too strong, but still forms a bond nonetheless. So this is kind of how ionic bonds work. Let's do another one. So let's do I don't really know how complicated they'll get, so I'll do a classic, sodium chloride. Actually, we just did a chloride one. Let's do sodium bromide. Okay, so sodium as an atom is 281. So it only has one valence electron. Bromine is 2887. Make sure that's right. That should be right. Wait, no, it's not. 28187. So it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. So sodium as an ion is +1, and bromine as an ion, ions are charged, is -1. So sodium is going to take that electron and transfer or donate it to bromine, making sodium +1 and bromine -1. Now, some of you might be wondering, wait a minute, you're not showing sodium with 8 valence electrons. Doesn't it want 8 to be stable? Well, when it loses that 1 here to become charged, look how many is left. 8. We don't show that in the drawing because when you draw dot structures, you're showing how many electrons are in the last energy level. Since you have donated that electron out of the last energy level, there is no longer electrons occupying that energy level. So it's just convention to leave it blank. So these are ionic bonds. These are formed from ionic compounds, a metal and a nonmetal. They transfer electrons to each other. One will donate the electrons, the other will accept it. The positive one is always the donor. The negative one is always the acceptor. Don't forget about table E when you're thinking of ionic compounds here. Table E has a couple of positive ions that are not metals. So ammonium, don't forget about him. He can also form ionic bonds because it has a positive charge. So I'm not really going to be concerned with the dot structures, but do keep in mind if you have a positive ammonium, it can bond with a negative ion like oxygen and form an ionic bond, not a covalent bond. So this, when they bond and you crisscross the charges down, just the numbers, you get ammonium oxide. That's an ionic bond. It's only nonmetals, but it's still ionic because of the charge attraction. Opposite charges attract. Never do this. That is a covalent bond. That is a sharing of electrons. Ions do not share electrons. So never show an ionic compound bonding with a line, because the line represents sharing electrons, which ionic compounds do not do. All right, let me make sure I covered everything I wanted to cover. Electronegativity kind of plays a role here, but I'm going to talk about that more probably tomorrow, or maybe at the end of the video, how electronegativity plays into this. Not tomorrow. My next video is Monday, and that's on the periodic table, which usually tends to be a shorter unit, so it shouldn't take very long to summarize. So we'll see where we end tonight. I don't want to go into too much, especially with polar and nonpolar being such a pain in the butt for the next video, but let's see how we're doing on time when we get there. All right, I'll talk about covalent bonds, then we'll do drawing covalent bonds, and then I will mention electronegativity, and then I think we'll call it a night. So, covalent. A covalent bond is seen in molecular compounds and these are two or more nonmetals. Either way, when you look at the formula, it will always be nonmetals. So, when you're drawing covalent compounds, this is a trick. If you go on further in your chemistry careers, this will not help you draw dot structures of a covalent compound. But in Regents chemistry, this is perfectly fine. Let's do a classic. Let's do water. Water is H2O. I'm going to get the dot structures of the atoms of water. The two H's each have one valence electron, because hydrogen only has one valence electron. And then oxygen is 2-6. So oxygen is going to be 1, 2, 3, 4, 5, 6. Every atom wants to have 8 valence electrons. Covalent compounds get there by sharing electrons. So, when we look at hydrogen, hydrogen electron to share. Oxygen also has 2 electrons to share, 1 for each hydrogen. So, they're just going to partner up. And then when you do that, make sure you clean it up. Make it look pretty. H, and there's a few ways you can show this. You can show the electrons being shared like this. Or you can show it in a bond. And that is water. Let me work through what I just did again, maybe using different colors so you can see it better. The hydrogens, I will do in orange. Orange, orange, I don't care how you pronounce it. And the oxygens, I'll do in red. Again, they each have a lovely 1 electrons on each hydrogen, and the oxygen has 2 electrons, just ready to share with somebody, looking for a friend. Please partner up with me. So, partner them up. The hydrogens will share their 1 electron with the oxygen, and you will form a molecule of water. Water always is drawn bent. We say this structure has a bent geometry. So, there's a few geometries we need to know when drawing compounds. I'm going to do all the ones you need to know tonight. So, water is bent because it has the central atom, the oxygen, the central atom, has 2 lone pairs, meaning it has 2 pairs of electrons that are not paired with another atom. They're just paired with each other. So those electrons cause a little repulsion of the hydrogens and just causes them to just bend down a little bit. So you will always draw water bent. The next one that has a different geometry is ammonia, NH3. But again, let's just use the tricks. H, H, H. Nitrogen is 2-5. 1, 2, 3, 4, 5. Would you look at that? H, each has a buddy looking to pair up. N has 3 buddies looking to pair up. Let's pair them up. So, for N, has those 3 lonely dudes looking for a friend. And H is like, I'll be your friend. And there you go. You have ammonia. So, when you're drawing these structures, take your time. That's the #1 thing I tell my students. You're going to want to rush into drawing them, and there's no reason to rush. No reason to rush. Take your time when you're drawing these compounds. If you're an atom, just take the time to draw them as individual atoms, and then just pair up the lonely electrons with each other. When you have 1 lone pair on your central atom, and you have those 3 other ones surrounding it, this is called a trigonal pyramid. I can't spell. Let's try again. Trigonal pyramid. Now, in terms of like how important is it to know these shape names, it's hard to say. Some years they like to ask questions about them, some years they don't. I don't remember the last time they asked a question on the shape names, so I'm just playing it safe and putting it on there anyway. But there's no that. Drawing them is definitely important. You need to know how to draw compounds, and you need to know how to draw atoms and ions for sure. Definitely need to know how to draw atoms and ions. They love to ask you to draw ions. Shape names, good to know. I don't know how popular they are as a test question, so we'll just play it safe. All right, let's do a big one. Carbon dioxide. C is 2-4. 1, 2, 3, 4. You have 2 oxygens. No, different colors. You have 2 oxygens, and we've done oxygen enough to know that they have 6 valence electrons. Would you look at that? Carbon has 4 to share, and each oxygen has 2. So pair them up. This one's going to look a little different than the other ones. We're going to have a double bond. So oxygen has 2 to share with 2 on carbon. Ooh, that's a double bond. And then the other oxygen also has those 2 to share. Clean it up if you want. Show it with bonds. Double bond C, double bond O. Yeah. Now, when you look at the central atom, in this case carbon, there's no lone pairs. Linear. This is just a straight line. Lovely straight line. Carbon dioxide. Double bond. Okay. Let's do one with a triple bond. Let's do N2. So N is 2-5, and there's 2 of them. So we got one like this. And the other one also looks like that. 1, 2, 3, 4, 5. Those each have 3 electrons each to share with each other. Let's share. So this first N has 1, 2, 3 to share. And the other N also has 1, 2, 3 to share. Since there's only 2 atoms, you have no choice but to be linear. There's 2 atoms. Linear, and this is a triple bond. All right, one more to draw. Let's do carbon tetrafluoride. Carbon's 2-4, fluoride is 2-7. So we got carbon with 4 to share, and then each, I'm not going to draw 4 fluorines. Each fluorine has 1 to share, and there's 4 of them. Would you look at that? 4 lonely dots on carbon, 1 lonely dot each on my 4 fluorines. Let's pair them all together. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. For each atom to have 8. So if I count, this fluorine has 2, 4, 6, 8. Not now, Mrs. G. You're going to have to wait. The other fluorines have 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And what about the carbon in the middle? Well, I spy with my 2 eyes 2, 4, 6. Every atom has 8. Woo! We're happy. And the same is true for all of these. So if you check all of them, 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And then the carbons has these 8 right here. 2, 4, 6, 8. Ammonia. 2, 4, 6, 8. This brings up a great point. Hydrogen is happy with 2. Hydrogen is happy with 2 valence electrons. And each hydrogen in this formula has 2 valence electrons. So that's 8. Hydrogen's happy with 2. Lithium's happy with 2. Beryllium's happy with 2. Helium is happy with 2. So the really small atoms are like 2's enough. Chill. I don't need 8. Like, come on, 2 men. What are you doing? And then water here, again, 2, 4, 6, 8 on the oxygens, 2 each on the hydrogens. No. Uh-oh, my battery's going to die. That's okay. I'm almost done. So, what is this structure? This is called a tetrahedral. Tetra means 4. Tetrahedral structure. So when you have one atom in the middle, bonded to 4 other dudes, we say tetrahedral. And you got to say it like that or you're wrong. Trying to think if there's anything else I really want to do tonight. I really don't want to get into polar and nonpolar. I'm tired. It's a 4-day weekend. That's just, polar's hard. I might save that for next time. Yeah. I can do polar and nonpolar, IMFs. Goodness. Bonding is a beast. This is a beast of a unit. This is so much. I guess I'll just mention electronegativity and then call it before my iPad dies, because I realized I didn't charge it because I'm a silly goose. Okay, so let's do a quick summary. We did ionic compounds. So first, chemical reactions. Form new things. Form new things. Form new things. So they're forming compounds or breaking compounds, which are chemically combined in a fixed ratio. If you break a bond in a chemical reaction, you absorb energy. When you form a bond, like in this reaction, you release energy, aka exothermic. This one broke a bond that absorbed energy, aka endothermic. Octet rule. All atoms would prefer to have 8 valence electrons except the small guys. Hydrogen and helium are more than happy with 2. Lithium and beryllium are also happy with 2. Drawing dot structures. Check their electron configuration on the periodic table. Those are the valence electrons. Draw them using a dot structure. 2, 1, 2, 3, 4, 5, 6. Ions. Take into account the charge. You need to write the charge to get credit. So, if oxygen normally has 6 valence electrons, it means it's gained 2 negatively charged electrons. Electrons are negative, so show it now with 8 instead of 6. Ionic bonds involve a transfer of electrons between a positively charged species and a negatively charged species, which is 9 times out of 10 a metal with a nonmetal. So, calcium will transfer its electrons to chlorine. Calcium's a metal, chlorine are your nonmetals. They are bonded because of the attraction of their charges. Their positive and negatives attract, opposites attract, so they form a bond, an ionic bond. NH4 is on table E, so don't forget about table E for your ionic compounds. They're all nonmetals, but a few of them are positively charged, so can form an ionic bond with a negatively charged thing. Never show ionic bonds with a dashed line or a dash. Never do this. That's bad. That's a covalent bond because that is showing a sharing of electrons. Ionic bonds transfer electrons. Transfer. Covalent bonds are found in molecular compounds, which is 2 or more nonmetals, like water, and they will share. So you just draw their individual dot structures and pair up the lonely electrons, which are represented using dots. Water will always be bent. Ammonia is trigonal pyramid. Carbon dioxide is linear. Nitrogen is also linear. And carbon tetrafluoride is tetrahedral. All right, where does electronegativity play into all this? So you can look up electronegativity on table S. We will define electronegativity more in depth later, but electronegativity is just attraction for electrons. Where the higher the En is, the higher the electronegativity, the higher the attraction is for electrons. If the I think we said if like the electronegativity difference is greater than 1.7 or some arbitrary number, you will form an ionic bond because one of them is so electronegative it literally pulls the electrons away from the other one, which will usually just be a metal. So if you look at one that I did earlier, which was calcium chloride, if you look up calcium on table S, calcium's electron configuration or electronegativity is 1. Chlorine's electronegativity is, it's right above it, 3.2. I already highlighted it. So 3.2 minus 1.0 is 2.2. That's greater than 1.7. That's an ionic bond. Chlorine is so electronegative that it literally pulls the electrons away from calcium. But a covalent bond, and we'll define it more tomorrow, has an En difference, or Monday, less than 1.7. So if you have an En difference less than 1.7, an electronegativity difference less than 1.7, that's covalent, which means one of them does not want the electrons more than the other. One is not more or greedier. One is not as greedy as the other. So they just kind of meet in the middle and say, we'll share. So for example, water was 2.2 for hydrogen and 3.4 for oxygen. And when you subtract those differences, you get 1.2. That's less than 1.7. That gives you a covalent bond. I think that's a good place to end it for tonight, because bonding is a beast, and drawing these it takes a while. And I don't feel like going over polar and nonpolar yet. I'm going to save that for next time. So next video, we're going to do polar and nonpolar, IMFs, and then periodic table really doesn't take very long. Periodic table. All right? Have a great night, everybody. I will see, hopefully, so many of you tomorrow who couldn't be more excited for spring.